Good afternoon, everyone. So for today's topic, we will talk about solvent extraction. What is solvent extraction? Solvent extraction is also known as liquid-liquid extraction and partitioning. It is a method to separate compounds and metal complex based on their relative solubilities into different immiscible liquids. It is usually water and an organic solvent. Immiscible liquids that we are talking here are those that cannot mix up together and separate into two layers when shaken together. Solvent extraction, in other words, is an extraction of a substance from one liquid to another liquid phase. Remember that the phase that we are talking here refers to a distinct region with a different composition than another region of the system.
Basic principles of solvent extraction method. Solvent extraction method is the method of transferring solute substance from one liquid phase into another liquid phase according to the solubility. It signifies that we can use another liquid in order to extract or separate the solute being mixed in a liquid phase. But before we can do that, we need at least two immiscible liquids. When we say immiscible, these are the liquids that cannot be mixed together. Usually, the liquid phases used in solvent extraction method are the aqueous solvent, also called as the water-based solvent, and the organic solvent, which are immiscible with each other. When we put water into the oil and shake the mixture together, most of the sugar substances from the oil will move to the water phase. That is because sugar is more soluble in water than in oil, causing the water to taste more sweeter than the oil after the extraction process. The solute substances to be extracted has a different level of solubility in the aqueous and in the organic phases. And that measurement of solubility will determine which liquid phase can extract more solute. That is because the more soluble substance is in a liquid, the more substance that liquid can extract. Let's say, for example, in order to extract sugar substances mixed in oil through solvent extraction method, we need another liquid that is immiscible or cannot be mixed with the oil. And the most common liquid for that is water. In order to check the efficiency of the solvent extraction process, we need to use this formula. This is the formula to know the remaining fraction of solute substance in phase 1 after a number of extractions. This formula was derived from the formula of partition coefficient, which is K is equals to the equilibrium constant of the solute partition in phase 2 over the solute partition in phase 1. Let's discuss how this formula was derived. The formula for partition coefficient is the start of this. Now, we must write the partition coefficient in terms of concentrations by substituting the concentration value of S1 and S2 in that formula. Concentration of solute in phase 1 is equals to Q times M over the V1, while the concentration of solute in phase 2 is equals to 1 minus Q times M over the V2. Substituting that concentration value of S1 and S2 in the formula of partition coefficient will give us this equation. Simplifying it will give us K is equals to 1 minus Q times V1 over Q times V2. From this formula, we can get the formula for the Q in order to check the extraction efficiency. And deriving it will give us the formula for Q, which is this. Here, Q represents the fraction of the solute remain in phase 1 at equilibrium. V1 represents the volume of liquid in phase 1, V2 is the volume of liquid in phase 2, K is the partition coefficient, and N is the number of extractions. Now let us try a sample problem involving solvent extraction. Here's the sample problem. Solute A has a partition coefficient of 3 between the toluene and water, with 3 times as much in the toluene phase. Suppose that 100 ml of a 0.010 moles of aqueous solutions of A are extracted with toluene. What fraction of A remains in the aqueous phase if one extraction with 500 ml is performed, or B, if 5 extraction with 100 ml are performed? Let us first solve for the situation letter A. Write all the given values, which are partition coefficient is equal to 3, the volume of phase 1 is 100 ml, the volume of phase 2 is 500 ml, and the number of extraction is only 1. We need to find the Q, or the fraction of solute remaining in the phase 1 after the extraction, using this formula for Q, which is this formula. Substitute all the given values in the formula, and that will give us 100 over 100 plus 3 times 500. And solving it will give us 0.0625, or approximately 6.3%. That means that 6.3% of solute A was remained in aqueous phase after one extraction using 500 ml toluene. Let's proceed on solving for the situation letter B. Again, write all the given values, which are K is equals to 3, V1 and V2 are both equal to 100 ml, and the N, or the number of extraction, is 5. Find the Q using the formula for it, which is this. Substitute all the given values to the formula will give us 100 over 100 plus 3 times 100 raised to 5. And solving it will give us 0.00098, or approximately equal to 0.1%. That means 0.1% of solute A was remained in aqueous phase after 5 extraction using the 100 ml toluene. From this result, we can conclude that it is much better to do few small extraction than one big extraction to make sure the efficiency of extraction process. However, there are some factors that might affect the extraction, and one of it is the pH level. When we say pH, it is the quantitative measures of the acidity or basicity of aqueous or other liquid solutions. The pH level of the solute might affect the extraction process because pH level can change the charge of the solute. If a solute is an acid or base, its charge changes as the pH is changed. If the solute becomes a neutral species, then it is more soluble in an organic solvent. But if the solute becomes charged, it is more soluble in aqueous solvent. That means that the partition of solute substance between phases changes as the pH level changes. That's why it is not advisable to use the K, or the partition coefficient, when there's acid or base involved in the extraction. In this case, instead of partition coefficient, we need to use the distribution coefficient, expressed as D is equals to the total concentration in phase 2 over the total concentration in phase 1. Since the total concentration in phase 2 is equals to B2 and the total concentration in phase 1 is equals to B1 plus BH positive 1, then the distribution coefficient will become like this equation. However, that is not the final formula because we need to find the formula for the base and for the acid since these two are different. To get the formula for the distribution of base and acid solute, we need to substitute these different variables. And that will give us the formula for the distribution of base into two phases and the formula for the distribution of acid into two phases. To check the extraction efficiency of the base or acid, we can use this formula for the Q. But since we are dealing with acid and base, which involve pH level, we must substitute the K here into D, or the distribution coefficient. Okay, now let us try a sample problem involving pH in solvent extraction. Here's the sample problem. Suppose that the partition coefficient for an amine, or B, is K is equals to 3, and the acid dissociation constant of BH positive is Ka is equals to 1.0 times 10 raised to the negative 9. If 50 ml of 0.010 moles of aqueous amine are extracted with 100 ml of solvent, what will be the formal concentration remaining in the aqueous phase? A at pH 10 and D at pH 8. Let us solve for the letter A first. Take note first the needed given values, which are Ka is equals to 1.0 times 10 raised to the negative 9. The pH is equals to 10. The H positive is equals to 10 raised to the negative pH, which is 10. So that will be 10 raised to the negative 10. V1 is equals to 50 ml. V2 is equals to 100 ml. And the moles, the number of moles of amine is 0.010. Okay, solve for the distribution coefficient. But take note that the solvent used is amine, and amine is an example of base. So use the formula for the distribution coefficient of the base, which is this. Substitute all the given values in the formula, and that will give us 3 times 1.0 times 10 raised to the negative 9 over 1.0 times 10 raised to the negative 9 plus 10 raised to the negative 10. And solving it will give us the result of D, or distribution coefficient, is equals to 2.73. Now we can already find the concentration of the remaining amine in the aqueous phase using the formula for Q. Substitute all the given values in that formula and then solve for it, and that will give us the result of 0.15 Q. Therefore, the formal concentration remaining in the aqueous phase at pH 10 is 15% of the 0.010 moles of amine, which is equivalent to 0.0015 moles of amine remain in the aqueous phase after the extractions. Now we can solve for the letter B. First, write all the given value. K is equals to 3, Ka is equals to 1.0 times 10 raised to the negative 9, pH is equals to 8, H positive is equals to 10 raised to the negative 8, V1 is 50 ml, V2 is 100 ml, and the moles, or the number of moles of amine, is 0.010. Solve for the D, or the distribution coefficient, using this formula. Substitute all the given values in the formula, and solving it will give us D is equals to 0.273. Now we can already solve for the Q using the formula for the Q. Substitute all the given values in that formula, and then solving it will give us the result of Q is equals to 0.65. Therefore, the formal concentration remaining in the aqueous phase at pH 8 is 65% of 0.010 moles of amine. It is equivalent to 0.0065 moles of amine was remained in the aqueous phase after the extraction. So, based from the results, we can conclude that to extract base with high efficiency, we must increase the pH of the aqueous phase.
Extraction of metal chelator. Most complex that can be extracted into organic solvent are neutral. Charged complex are not very soluble in organic solvent. One scheme for separating metal ions from one another is to selectively complex one ion with an organic ligand and extract it into an organic solvent. So because charged species are more soluble in water than organic solvents, we need to remove the charge from the charged species to extract water into an organic solvent. One way we can separate metal ions aqueous phase solution from one another is to selectively complex one ion with an organic ligand and extract the complex into an organic solvent. We can use weakly acidic ligands such as diazone, 8-hydroxyquinoline, and Cafferon. So we have here protonated ligand in an aqueous phase losing a proton to become L negative. And then some number of L negative will react with our metal ion here, Mn positive, to form our metal ligand complex. The acid dissociation constant over ligand is here, and the beta here is the formation constant of our metal ligand complex. For example, we got here a dense organic phase. Perhaps this is a trichloramethane down here, and up on the top, we got our aqueous phase. We can see that in the aqueous phase, we have a couple of equilibria occurring. We have an equilibrium between our ligand and proton being protonated and deprotonated. We've got then ligand reacting with our metal ion to form the complex, and then this large arrow down showing that metal ligand complex is much more soluble in our organic phase than the water phase. And also, we get our protonated ligand to dissolve into the organic phase. The partition coefficient for the ligand and complex are given here. So we have the equilibrium between the protonated ligand in the aqueous phase and the protonated ligand in the organic phase. And the partition coefficient K sub L is equal to the concentration of our ligand in our organic phase divided by the concentration of our ligand in the aqueous phase. And they are both protonated ligand. So we also have the equilibrium between the metal ligand complex in the aqueous phase and the metal ligand complex in the organic phase. So across that phase boundary, that partition coefficient K sub M is equals to the metal ligand complex in the organic phase concentration divided by the metal ligand complex in the aqueous phase concentration. We can combine these two equations to give us this equation down here, where we have the concentration of our metal ligand complex in the organic phase is equals to the K sub M times the concentration of our metal ligand complex in the aqueous phase, which is equal to K sub M times beta times the concentration of our metal ion in the aqueous phase times concentration of our ligand in the aqueous phase. We can solve the acid dissociation expression for ligand for concentration of the deprotonated ligand in the aqueous phase, and then substitute that in the equation here. So we plug that expression and we rearrange to get this one. We can plug that value to the distribution coefficient expression, and it gives the distribution coefficient is approximately equal to K sub M times beta times n power of our K sub M times the concentration of our protonated ligand raised to the nth power in the aqueous phase divided by the hydrogen ion concentration in aqueous phase. But most of our protonated ligand is in the organic phase, and that means that we can substitute the concentration of our protonated ligand in the aqueous phase with the concentration of the ligand in the organic phase divided by the partition coefficient of the ligand, and that means that our distribution coefficient looks like this. Thus, the distribution coefficient for metal ion extraction depends upon the pH and the ligand concentration. For example, we have here a chart plotting the percentage extracted as a function of pH. And we can see that the different metals, these curves are approaching 0 to 100 at a significantly different pH. Thus, if we want to say separate tin from lead that already use a pH somewhere in between there.
There are three methods of extraction: batch extraction, continuous extraction, and countercurrent extraction. These three basic methods of liquid-liquid extraction are generally utilized in the analytical laboratory. The first one is batch extraction. Batch extraction is the simplest and most commonly used method. It consists of extracting the solute from one immiscible layer into another by shaking the two layers until equilibrium is attained, after which the layers are allowed to settle before sampling. This is commonly used on the small scale in chemical laboratories. The most commonly employed apparatus for performing a batch extraction is a separatory funnel. A separatory funnel consists of a conical or pear-shaped glass body with a stopcock and a stopper on top and is used to separate immiscible liquids. When two immiscible liquids are placed in a separatory funnel, two layers are seen. The denser solvent will be at the bottom layer. The batch extraction may also be used with advantage when the distribution ratio is large. The second method of extraction is the continuous extraction. It makes use of a continuous flow of immiscible solvent through the solution or a continuous countercurrent flow of both phases. Continuous extractions are particularly applicable when the distribution ratio is relatively small. Continuous extraction device operates on the same general principle, which consists of distilling the extracting solvent from a boiler flask, condensing it, and passing it continuously through the solution being extracted. The extracting liquid separates out and flows back into the receiving flask, where it is again evaporated and recycled while the extracted solute remains in the receiving flask. When the solvent cannot easily be distilled, a continuous supply of fresh solvent may be added from a reservoir. Continuous extraction requires a special kind of extractor depending on whether the solvent used for extraction is lighter or heavier than the sample solution. This extractor is called Soxhlet extractor. The last method of extraction is the extraction by continuous countercurrent. Countercurrent extraction, discovered by Lyman Craig in 1943, is a multiple liquid-liquid extraction technique involving two immiscible liquids in which the separation of the components occurs based on the difference in their solubilities in the individual phases. The separation through continuous countercurrent method is achieved by virtue of the density difference between the fluids in contact. The choice of method to be employed will depend primarily upon the value of the distribution ratio of the solute of interest as well as on the separation factors of the interfering materials. With the help of this method, we can have accurate quantitative analysis of a single as well as the mixture of the components. The extractor consists of 300 to 400 such chambers. The organic solvent in the aqueous solution are now introduced in tube A and then passes to B. It is shaken and is allowed to attain the equilibrium. Now the apparatus is tilted so that the upper layer gets decanted through C and is collected in D. When the apparatus is again made vertical, the liquid passes through D and E in the next chamber of A and then to B. The process is repeated until the two liquids gets almost separated.
Classification of extraction system is the process of metal extraction is based on the formation of neutral metal chelate. All types of chelating agents find useful application in metal extraction procedures. This various extraction system can be classified in several ways. The classical one is based on the nature of the extracted species. The present-day classification is based upon the process of extraction. The classification of extraction system is based upon the process of extraction. Thus, based upon the process of extraction system can be classified into four major classes. The first classification of extraction system is chelate extraction. This extraction proceeds by the process of formation of chelate or close ring extraction between the chelating agent and the metal ion to be extracted. The best example for this first classification of extraction system is the extraction of uranium with 8-hydroxyquinoline in chloroform, and the second one is the extraction of iron with copperon in carbon tetrachloride. The second classification of extraction system is extractions by solvation. In this classification, the extractions proceed by the process of solvation of the species which is extracted into organic paste. Oxygenated organic solvents such as alcohols, ketones, ethers, and esters show some basicity because of the ion pair of electron on the oxygen atom and can therefore directly solvate protons and metal ions and bring about their extraction. The example for this is the extraction of uranium with tributyl phosphate from nitric acid, and the second one is the extraction of iron with diethyl ether from hydrochloric acid. The third classification of extraction system is extraction involving ion pair formation. This classification, the extraction proceeds with the formation of neutral uncharged species which is in turn gets extracted into organic paste. The best example of this is the extraction of scandium and uranium with tributyl amine from mineral acids. In this case, an ion pair is formed between complex of metal ion with high molecular weight, amine, and anionic species of mineral acids. And the last one is synergic extraction. In this case, there is enhancement in the extraction on account of use of two extractants. Example, the extraction of uranium with tributyl phosphate or TBP, as well as the 2-thionyl trifluoroacetone TTA. When we say tributyl phosphate is an organic liquid solvent used in the extraction of uranium in plutonium salts from reactor effluents, as a solvent for nitrocellulose and cellulose acetate, and as a heat exchange medium.
Primary requirement of solvent extraction for separation or removal purposes is a high distribution ratio of the solute of interest between the two liquid phases. It is useful to employ a number of different techniques for enhancing the distribution ratio. Some of the factors which affect the distribution of solute of interest are the following: choice of solvent, salting out agents, variation of oxidation state, use of masking agents, modifiers, and lastly the pH value. The most important consideration in the selection of a solvent for use in a particular extraction procedure is the extractability of the element of interest. I have here a list of an ideal characteristics of solvent. First, organic solvent should have high distribution for solute. It means solute should be more soluble in solvent, while the solubility of undesired components like impurities should be low. The next one is low solubility in aqueous phase. Either it should be completely insoluble in water or it should be slightly soluble. The third one is low toxicity and inflammability.
means it should not create or catch fire. Sufficiently low viscosity. Viscosity means the state of being thick and semi-fluid in consistency due to internal friction. The viscosity should be very much low because we have to mix it with aqueous layer and we have to shake it. So if it is viscous, the process cannot be performed accurately. Sufficient density difference from aqueous phase. It means there should be a proper difference in density between the two solvents, which are the organic and aqueous, because they have to be separated from each other. Then, it should be chemically inactive, meaning the choice of solvent should not react with each other. Of course, the solvent should be cheaply available. It should be cheap because in this process we may also lose our solvent. Lastly, it should be easy to recover. Another factor is salting out agents. The function of salting out agent would be primarily of providing a higher concentration of complex and thus improve the extraction. Extraction of metals can be enhanced by adding high concentration of salt to aqueous phase. For example, we are going to extract some metals in organic phase, so this extraction can be enhanced by addition of some salt in aqueous phase. There will be increase in concentration of ions in aqueous phase. In this way, the extraction of the metal interest will be increased in organic phase, and this is called salting out effect. Another factor is the oxidation state. The selectivity of extraction sometimes may be increased by modifying the oxidation of metal, which means if we modify the oxidation state of metal, we can also change the extraction efficiency. For example, extraction of iron from chloride solutions can be prevented by reducing iron 3 to iron 2, which does not extract. Meaning, if we want to have greater efficiency, we must keep iron in +3 state. It is important in the preparation of the solution for extraction to adjust the proper valence state of metal ion required for the formation of the complex in order to ensure complete extraction of that element. Another factor is the use of masking agent and the extraction procedures for metal pairs that are difficult to separate. Masking or sequestering agents are introduced to improve the separation factor. In solvent extraction, masking agents are used to prevent certain metals from forming extractable complexes and increasing the selectivity of the method. There are various masking agents that are being used, and this includes cyanides, tartrates, citrates, and fluorides. Modifiers are the additives to the organic phase to increase the solubility of the extractant in diluent. So sometimes these chemicals are added in organic phase, which increase the solubility of the component in organic layer. And for this purpose, high molecular weight alcohols, for example, capryl alcohol, is commonly used as modifiers. Lastly, the process of liquid extraction largely depends on pH value. The extraction efficiency of different solute varies upon the pH value.